In periodic orbit theory, we make predictions about the infinite time behavior of dynamical systems, a long time compared to Lyapunov time or to any characteristic time of the system. And we do this by computing short time periodic orbits. Now, how is that possible? How can I use short periodic orbits to describe dynamics at very infinite, very long times, which in principle are not accessible to computation? The key idea is the idea of shadowing. And in this short video, we will illustrate shadowing by looking at three periodic orbits. A short one, another short one, and then a long one, which in some sense is the concatenation of these two orbits. And what's amazing, as you'll see in the video, that the long orbit is shadowed very closely, and I mean very closely, for most of the time, by the two short periodic orbits that we have no difficulty computing because they're short. The reason why these orbits are very close is because all three orbits are exponentially unstable. So even if you start very close to any pair of these orbits, they will of necessity have to separate at some point because they separate exponential rate. If they track each other for a long time, it means at some point they have to be extremely close to each other because otherwise they couldn't stay together and exponentially separate in time at the same time. The example comes from Kuramoto-Sivashinsky equation computed on a finite domain. It's a system in which we have between 40 to 60,000 periodic and relative periodic orbits. So we have a very rich repertoire of these orbits. And here we start with two orbits, one of the short period and the other one of the long period. What you see in the beginning is that they have been started along the two periodic orbits at two very nearby periodic points, and for a while they track each other very accurately. However, at this moment, they start separating, they diverge. And one of them just goes off, the long periodic ones, and does an extra twiddle, but then an amazing thing happens. It comes back, and having completed the twiddle, it tracks the short orbit and returns to the same initial point as the previous one. In other words, the long periodic orbit is being shadowed by the short ones, and we can use computation of the short ones to estimate the properties of the long ones. And this is the basic idea behind periodic orbit theory. Short periodic orbits, which are there for infinite time because they're invariant sets of the dynamics, are actually the building blocks from which all more complicated ergodic behaviors are built.